The first lesson in the exponential growth decay unit. These are all application problems, and we're going to use some of the skills that we developed in Unit 7. But what you're going to be most happy about is probably the fact that we're going to now have calculators back again, and you're definitely going to need them. So be sure that every lesson that you do, any kind of practice that you do, that you got a calculator, scientific calculator. It doesn't have to be a graphing calculator, but you have to have one that has the logarithm buttons on it, because that's what we're going to be using for a lot of these questions. So 8.1 is pretty basic exponential growth and decay. Here is the formula for 8.1. Each of the 4 standards will have its own formula that we'll use. This is, I just call it the knob formula, NOB. I think about it like that. I've outlined what each of these variables stands for. This is the ending amount. This is the starting amount. We've got the rate of growth. One thing to keep in mind, if this rate is 1, that means it's 100% of itself. If it is decreasing or decaying, you'll need to take that rate as a decimal. For instance, 5% would be 0.05, and you'll need to subtract it from 1. So if something is decaying at 5%, B will be 0.95. If it is growing at 5%, B would be 1.05. Growth would be adding to 1, decaying would be subtracting from 1. T is the time for the starting amount to become the ending amount. That's what the numerator T represents. K, which is the denominator of the exponent, T over K is the exponent for B. It is the time for this rate to occur. So I've got 3 different examples. They'll all be solving for a different part of the equation. First one. So bacteria is doubling every 6 hours. How long will it take for 400 bacteria to become 1 million? So we've got all of the variables except for one of them. Let's refer to the question. How long will it take? Well, how long will it take is going to be in our exponent, because these are the 2 values of time. These are both amounts. This is a rate. These are both related to a time. So how long is it going to take for the bacteria that is doubling every 6 hours? So let's see what we've got. Do we have an ending amount? Ending amount is 1 million. Do we have a starting amount? 400. Do we have a rate? Our rate is that it's doubling. That's 200%. So I use 2. Do I have the time that it takes for the starting amount to become the ending amount? I do not. That's the question. How long is it going to take for the starting amount to become the ending amount? Our unknown is the T, and our K is time for the rate to occur. Well, it doubles every 6 hours. Since the unit of that time is in hours, our numerator unit is going to end up in hours as well. So I started out with actually maybe one of the more difficult problems, because the unknown is in the exponent. Here is something you need to keep in mind. You must use logs if the unknown is in the exponent. you will realize that you have to use logs if the unknown is in the exponent. And so we're solving for the exponent, which means I need to isolate the part that is being raised to the exponent. So my first step will be to divide by the 400. And so we'll use our calculator. 1 million divided by 400 is 2,500. So 2,500 bacteria, well, it's not 2,500 bacteria anymore because that's canceled out, is equal to 2 to the t over 6. This is an exponential equation. And so in order to solve an exponential equation, I'm going to turn it into a log equation, which means log base 2, this is the base, of 2,500 is equal to t over 6. Well, in the last unit, we didn't learn about how we do calculations on our calculator with logarithms. And so what this becomes, it's called the change of base formula, and this is what you'll use your calculator, because your calculator is set up for a log with a base of 10. This is a log of base of 2. So the change of base is simply to take the log of 2,500 and divide it by the log of the base. The log of the big number divided by the log of the base is equal to t over 6. So log 2,500, make sure you close your parentheses, divided by the log of 2, and I get 11.2877. That's what's equal to t over 6. So how do you finish solving this with algebra? I'll multiply by 6 on both sides. And just take the answer that's already on your calculator and times it by 6. And so the time is approximately 67.7 hours. That's about how long it will take for these 400 bacteria to become 1 million bacteria. A little less than 3 days. Alright. Tatium decays so that 500 grams will be 3 grams in 100 years. What is its half-life? Now this seems like a question that it's not really clear about what the unknown is. This one was how long in the first question. That seemed to be a time. This one is also a time. It's asking you how long does it take for its half-life to occur. That's when it says what is its half-life, it means how long does it take for that half-life to occur. So we have a starting amount and an ending amount. The first problem was a growth problem because 400 was becoming 1 million. In this case, we're looking at decay because we had 500 and it has decayed to 3. The rate when it says half-life is 0.5. Half-life rate is 0.5. Then we've got 100 years. That's a time, but we have to determine, is it the time for 500 to become 3 or for this rate to occur? And it clearly is for the 500 to become 3. So we have that rate of 100 years over K. So what will the unit of K be? What will K's unit be? Well, it's got to be the same unit as the numerator. Those units have to be the same. If they're not, on occasion when you have both of them, you have to make conversions so that they are the same unit. So again, solving for the exponent takes us back to what I mentioned in the first one. You must use log if the unknown is in the exponent. That tells me I'm using logs to solve this problem. First step, anytime you have both the starting and ending amount, you will always start by dividing. Three divided by 500 .006 equals 0.5, which is raised to the 100 over k. This problem is very similar to the last problem until we get to the end. This becomes the log 0.006. It has a base of 0.5. That's equal to 100 over k. The log of 0.006, but it has a base of 0.5, which means the log of 0.006 divided by, this is the change of base formula, 0.5. That's equal to 100 over k. Now, what's different between this problem and the first problem is the unknown's in the denominator. So I cannot multiply both sides by 100 because my unknown would still be in the denominator, and I never want my unknown to be left in the denominator. What most of you, or a lot of you, probably don't realize is when you have a fraction equal to a fraction and it's a proportion like this, I can just turn it upside down on this side, as long as I do the exact same thing on the other side. Once I've done that, I can do what I did in the first example, which is to multiply both sides by 100. My unknown's in the numerator, and then it's just a matter of typing it into my calculator. So I'm going to take 100 times the log of 0.5. I'm going to be sure and close my parentheses. I went ahead and hit enter, and now I'm going to divide that by the log of 0.006. And I got 13.55. So a little more than 13 and a half. What is that unit? It's in years. That's what the unit of time was in the exponent. So the time was around 13 and a half years it's going to take for the half-life of Tatium. Now who's got time to wait for that? Alright, one more example. As promised, we'll be solving for something different within the equation. If the price of sneakers increases at 6% per year, how long will it take to double in price? Well, that almost seems like we've got two rates. We've got a 6% and we've got doubling. However, I'm missing what appears to be starting, ending amounts, times, all of that kind of stuff. So let's just see. Do I have an ending amount? Do I have a starting amount? Yes, in a way. It looks like I don't, because I don't see $50, $100, 30 cents, anything like that. But it does say that the price will double. So let's say if the price was 100 to start and it doubled in price, what would the ending amount be? 200. If the price was 75, the ending amount would be 150. It has doubled. It doesn't matter the prices, it's doubling, and so all you have to do is say 2 equals 1. What's my rate? It is increasing at 6% per year. As mentioned in the very beginning, when it's an increase, you add that percent onto 1, because 1 represents 100%, but it's growing at 6%. How long will it take to double in price? Well, this fraction has a t and a k, 6% per year. That means the k is for every year, and this is what we're looking for. Our unknown is in the numerator. So what would be my first step? Well, my first step would be to divide by the 1. So we're just going to have 2. I'm going to go on and have the log of 2. What's my base? Well, my base is what's being raised to the exponent over here. So it's 1.06 is equal to t over 1. So this one's fairly simple. The log of 2 divided by the log of its base is equal to t. Log of 2, close parentheses, divided by the log of 1.06 is 11.9. 11.9 what? Go back to your exponent. Time is in years. Almost 12 years it's going to take for that to double. Okay. I was looking for a problem where you were looking for the starting amount. Let's just set one up real quick. Let's just say we've got our equation, and I'm just making up numbers here just so you can see the math of it. And we've got 300. We are looking for NO. I'm going to say this one is decaying at 11% every 3 years. It became 300 pounds in 7 years. What did it weigh at the start? Okay, just made that up on the fly because I want you to see solving for NO. Alright, so let's go back and see. It's decaying at 11%. As a decimal, 11% is 0.11. I've got to subtract that from 1. That becomes 0.89. That's my B. My T is the time that it took for NO to become N. That was 7 years. And this decay was every 3 years. Should have made it more challenging and made you have a conversion in the exponent. Okay. When solving for NO, the first thing you do is not to divide by NO, but actually these are being multiplied, so I'm going to divide by this entire rate and exponent. I'm dividing this side by that rate to the exponent of 7/3. Now in the calculator, that's just going to require you to make sure you've got some extra parentheses probably. So 300 divided by, and then I'm going to put parentheses of 0.89. I'm going to raise that, and then I'm going to go ahead and put the 7/3 because it's a fraction in parentheses. 7 divided by 3, close my parentheses on that, hit enter, and I've got 393.7 as my answer. What's my unit? Well, NO is going to have the same unit as N, and so it's going to be pounds.